Here we go on 3.2. We're going to look at special kind of events, independent and mutually exclusive events. We're going to stick with this simple experiment of rolling a fair six-sided die and stick with our event A, even events, and B, even outcomes for A, and for B, outcomes less than 5. Let's find these two probabilities, probability of A and probability of A given B. Probability of A, we've already found this. We know that we take the number of the outcomes in A over the total number, so we get 1/2. And now probability of A given B. So we're now assuming that B has occurred, which from last time we recognize we're going to put in the number of outcomes in B, and in the numerator we put the number of outcomes that are shared in those. So we get 2 and 4 are the shared or the and outcomes for A and B. So that is 2/4. Okay, that also reduces to 1/2. All right, so we want to notice that we get equal values. Or in other words, the probability of A is equal to the probability of A given B. So it doesn't matter whether B has occurred or not. We get the same probability. Let's look at now some probabilities about B. Probability of B, well, there's 4 outcomes in B over the total of 6, so we get 2/3. Now, probability of B, but assuming that A has happened, so our new denominator is 3, and we want now the intersection, or I'm sorry, the and event between A and B, and then we know that there are 2 outcomes. So again, we get equal probabilities. That is, the probability of B is equal to the probability of B given A. So it doesn't matter whether A has occurred or not. We get the same probability for B. It stays the same. So when we have a situation like we had for this example where the probability of an event is the same whether another event occurs or not, we call those two events independent. So in our previous example, A and B are independent events because we had this relationship. The probability of A equaled the probability of A given B, and we also had the probability of B equal to the probability of B given A. If it works one way, it's going to work the other way as well. All right, so basically what that means is independent events happen when the occurrence of one of those events doesn't change the probability that the other one will occur. So it's independent, right? It's not linked to the other event. It's not dependent on the other event. Okay, so then on the flip side, dependent events are those that the occurrence of one does change the probability that the other will occur. So if we don't have this equality, then those events are dependent. So we could also say the same thing going the other way. If the probability of B does not equal the probability of B given A, then A and B are dependent. All right, so let's look at another example. Let's look at a standard deck of cards. 52 cards, 4 suits, clubs, diamonds, hearts, spades. Diamonds and hearts are red. Clubs and spades are black. 13 cards in each suit, going from 1 up to 10, and then Jack, Queen, Queen, and King. And I guess the other thing to note is 1 is typically referred to as the ace card. Okay, so we're going to look at 2 scenarios. This first one, we're going to look at selecting cards with replacement, and the other one, we will select cards without replacement. So suppose we pick 2 cards with replacement, and the first card is red. The probability of choosing a red card out of the whole deck of 52 cards is going to be 26 over 52, right, which is 1/2. Half of the cards are red. All right, now let's say we put that card back in the deck, we shuffle and we choose another card. Now, what is the probability of choosing a red card with the second one given the first card was red? Well, we put the card back, so we have the same probability, 26 over 52, so 1/2. All right, now let's look at the scenario where we choose two cards, but this is without replacement. The probability of choosing a red card the first time around is, all right, the same as what we got before, 26 over 52. All right, that's equal to 1/2. Now, without replacement means that we're going to pick the next card without putting the first one back and shuffling. So if that's the case, then we have only 51 cards to choose from. And if that first card was red, now there's only 25 cards left. And our probability is 25 over 51, which is equal to 0.490 or approximately 0.49. Okay, so it's different, right? We had probability of 0.5 that the first card was red, but given that we're drawing another time and the first card was red, we have a different probability. So we want to look at these two scenarios and determine which of these is representing independent events, and we can see that it's when we pick with replacement. So picking or choosing two cards with replacement. If we're asked if two events are independent, all right, we want to know, well, how do we test for that? Well, there's three different ways. We want to show that one of these three things is true, that the probability of A given some other event B is equal to A, probability of A, or we could go the other way where we look at the probability of B and see if that's the same as the probability of B given A. All right, now the other way we can test it is if the probability of A and B is equal to the probability of A times the probability of B. All right, this one, we haven't shown why this is the case yet, which we will get to in the next section, but we want to know that is one way to test for independent. So let's look at this example. Let M be taking a math class, S be taking a science class. Then M and S is equal to the event of taking a math class and a science class. Suppose we have those probabilities that are given, and we want to know, are these two events independent? All right, so just as a reminder, we want to show one of these three things to show independence or not. Okay, so let's look at the first one and figure out what the probability of M given S is. So just a little refresher, this is going to be the probability of M and S over the probability of, hopefully you're thinking it, S. So plugging in those values that are given to us, we got 0.3 over probability of S, which is 0.5. So we get 0.6. Okay, that is what we have for, that is equal to the probability, that's not going to fit there. That equals the probability of M. Okay, so we were able to show that the probability of M given S is equal to the probability of M. So that shows independence. So we can say yes. Now, we're going to go through the two other things just to show that they're all going to come to the same conclusion. All right, we're going to show that we get the same conclusion if we look at the other two. So let's look at the probability of S given M. So probability of, again, M and S goes in the numerator over the probability of M this time. So that's equal to 0.3 over the probability of M, which is 0.6. And that gives us probability of S given N, taking a science class, given taking a math class, equals 0.5, which is actually equal to the probability of S. So that also confirms that we have independent events. Now let's just check that third one. And let's take probability of M, math class, times probability of S, science class. Multiply those together. So we get 0.6 times 0.5. And we end up with 0.3, which equals the probability of math and science. So that one checks out as well. All right, we really only needed to verify one of them, but all three indicate that taking a math class, taking a science class are independent events. So let's look at Venn diagram in relation to a couple of events, C and D. And unfortunately, these got split onto two different pages. Going on to the next page. All right, let's look at, on this first one, look at event C or D, and then the second one we'll look at C and D. Okay, so if we are going to shade C or D, right, that's where we have an outcome in C, in D, or in both. So we're going to shade all of C and we're going to shade all of D. Okay, now what about C and D? There we're going to want to shade only the outcomes that are in both C and D. Well, there is nothing to shade because there is no overlap. Okay, when we have these two kind of events, that have no overlap, where there are no shared outcomes, we call those events mutually exclusive. They both exclude the other. So they're mutually exclusive. Okay, now let's just sort of think without actual numbers here. How would we find the probability of C or D? Well, since they're kind of stand alone, they don't share any outcomes, maybe it comes intuitively to say, we're just going to take the probability of C and then we're going to add it to the probability of D. That's jumping ahead a little bit to the next section, but you know, maybe at this point you can kind of see that intuitively. All right. And that's the best we can do. We don't have any numbers, so we're just going with the notation. But now, considering those same two events, C and D, that are represented here, all right, with no shading, what is the probability of C and D? What's the probability of them occurring at the same time? All right, well, hopefully, you know, it makes sense that that probability is 0. There are no outcomes that are in both C and D, so they cannot occur at the same time, so that has probability of 0. Okay, so let's formally look at definition of mutually exclusive. If A and B are mutually exclusive events, if they cannot occur at the same time, that means that A and B do not share any outcomes, and the probability of A and B is equal to 0. Okay, so let's look at another example here. We have a sample space that includes values, integers 1 to 10, and we're going to assume equally likely outcomes. And we're going to let A equal 1 through 5, B equals 4 through 8, and C equals just 7 and 9. Okay, so let's look at these other events, A and B. So we want outcomes that are shared. And it looks like they share 4 and 5. And let's look at the probability of A and B. All right, well, there's 2 outcomes over 10, so 2 over 10 or 1/5. All right, what about A, C? All right, A and C. Well, they share no outcomes, and so they have probability of 0. B and C? Well, there is 1 outcome, 7, that's in both of those. So the probability of B and C is 1 over 10. All right, so the question is, which pair or pairs are mutually exclusive? And hopefully we're seeing that A and C are mutually exclusive, and that is because the probability of A and C equals 0, and they do not share event. They do not share outcomes. Okay, one little other question in that example that almost gets lost there. Find an event. Find an event that is. We'll call it D. Let's get rid of that word. Find an event D that is mutually exclusive with B. All right. Well, there's a lot of options. Probably many options that we could come up with. One possibility. We just want an event that includes outcomes that are not included in that event B. So we could choose the event 1, 3, and that would be mutually exclusive with B. Okay, so now we're going to look at some other examples having to do with mutually exclusive and independence. We look at this next one. J and K are mutually exclusive. Probability of J is 0.35, probability of K is 0.15. The first question is on the next page. What is the probability of P and K? Okay, hopefully you're seeing that that is kind of a trick question, because if they're mutually exclusive, that probability is going to be 0. Okay, next question. Are J and K independent? Why or why not? Okay, we have to do a little bit of work here to figure out. So let's test to see if the probability of J equals the probability of J given K. All right, we're given that the probability of J is equal to 0.35. And does that equal the probability of J given K? Probability of K, that goes in the denominator, that's 0.15. And in the numerator, all right, we want that to be the probability of J and K, which we just figured out was 0. So that goes in there, 0. So that's equal to 0. So those are not equal. So that answers the question that no. And it's because what we just showed, that P, the probability of J, is not equal to the probability of J given K. Right, D and F are independent events. Probability of D given F equals 0.45. Find probability of D. Okay, little bit of a trick question there. Hopefully you're thinking about that. We have all the information we need. Well, if they are independent